Hi everyone, welcome to the fourth lecture of Chapter 4. Today we are going to talk about redox reactions. And redox reactions are a special type of reaction that involves the transfer of electrons. So we're going to learn a little bit about redox reactions today. We will cover them more in depth when we learn how to balance redox reactions in a later chapter. So in an ionic compound formation, we have electrons that are being transferred. They're leaving from the magnesium and, going to the oxygen. So magnesium loses those two electrons and forms the Mg2 plus cation, and oxygen gains those two electrons and forms the O2 minus anion. And it's really obvious to see the movement of electrons in an ionic compound because they are being fully transferred from one thing to the next. In a covalent compound or in a molecular bond, the movement of electrons isn't so clear because they're just kind of shifting towards one atom or the other. So when we have our hydrogen, right, H2, our diatomic hydrogen, the electrons in that bond are sitting directly in the middle because each of the hydrogens has the same electronegativity. If we look at the chlorine molecule, same thing, the electrons are sitting in the middle and the electrons are being evenly distributed because both of the chlorines have the same electronegativity. When we bond the hydrogen and the chlorine together, now we're going to have a difference in electronegativity. That chlorine is much more electronegative than the hydrogen is, so it's going to pull the electrons towards the chlorine, which makes the chlorine partially negative. That's what that little symbol means. That is the lowercase Greek letter delta, and it means partial. So we have a partially negative chlorine because the electrons are sitting closer to chlorine than they are to hydrogen. And we have a partially positive hydrogen because the electrons are being shifted away from it. So the electrons are not being distributed as equally in these bonds. And so this is why we start talking about this oxidation-reduction reaction. It gives us a way for us to talk about how these partial negatives and partial positives and where the electrons really are in the molecule. Are they sitting closer to one atom or another? So we need some terminology first. These reactions are called oxidation reduction, but we call them redox for short. Okay, so redox reactions and oxidation reduction reactions, those mean the same thing. So oxidation is the loss of electron. If something is being oxidized, it is losing electrons. And reduction is gain. So if something's being reduced, it is gaining electrons. Both of these have to occur at the same time, right? If something is gaining electrons, then they had to come from somewhere, which means that something else lost electrons. And if something is losing electrons, right, they just can't go into nowhere, something else must gain them. So if you have something that's being oxidized, you also have something that is being reduced. And the way that you're going to remember which one is which, you can remember either oil rig or Leo says Ger. So if you remember oil rig, it's oxidation is loss, reduction is gain. Or you can remember Leo says Ger, loss equals oxidation, gain equals reduction. Either way, but trust me, you're going to want a way to remember which one is which. So the first thing that we're going to do when figuring out whether something is being oxidized or reduced is we are going to assign oxidation states. And so these rules are in order of priority. So follow rule number 1, and if you still need more rules, then follow rule number 2. And if you still need more rules, follow rule number 3, and so on and so forth. Okay, so the first rule is that free elements, which means elements that are sitting by themselves, will have an oxidation state of 0 because they are in their elemental form. They haven't gained any electrons or lost any electrons, so our electron count essentially is 0. So sodium would be 0 by itself. Chlorine, you'll notice chlorine is one of those diatomic molecules, but since it's still only bonded to chlorine, those electrons won't be shifted left or right in the molecule because both of the chlorines are equally electronegative. So again, it's going to have an oxidation state of 0. So even if it's a diatomic, still just an element by itself, still going to be 0. If we have a monatomic ion, like Na plus or Cl minus, right? Or, even Mg2 plus, right? Something like that. If it's just an ion by itself, then their oxidation state is equal to their charge because their charge is telling us how many electrons they have lost or gained. So if we look at an ionic compound, right, an ionic compound we know will split into its charges, Na plus and Cl minus. So that means in this ionic compound, Na is a +1 and Cl is a minus 1. And just kind of a brief, key point is that when we have charges, we write the number and then the charge. So like Mg2 plus. When we have oxidation states, we write the charge and then the number. So like Na plus 1 and Cl minus 1. This is how you can tell the difference between charges and oxidation states. They are different. They have different uses, really. So make sure if you're writing a charge, we have a number and then the charge. If you're writing an oxidation state, you have the charge and then the number. So if we have an ion in their ionic compound, then their charge is going to equal their oxidation state. If we have something where it's not as clear and you're trying to figure out your mystery charge, you'll use 3A, where the sum of oxidation states of all the atoms in a neutral compound is 0. So like in sodium chloride, right? Sodium chloride is a neutral compound, and that means, right, our +1 and our -1, if we add them together, that's going to give us 0 for the entire molecule because it's not charged. If we have a polyatomic though, right, like nitrate, then all of the charges, or all of the oxidation states, are going to equal the charge on the polyatomic. So nitrogen is one that will typically change oxidation states. So a lot of times we'll actually have to solve for what the oxidation state of nitrogen is. Oxygen, and we'll see this later, oxygen is always going to have a -2 unless it's in peroxide, in which case it's going to have a -1. So we know oxygen is always going to be a -2, so we would have to solve for nitrogen in this case. And we would do it like a mathematical equation. Nitrogen plus, we have 3 oxygens, each with a -2 oxidation state, is going to equal -1, the charge on the polyatomic, because the nitrogen plus the oxygens have to equal the charge on the polyatomic. So then we'll get nitrogen -6 equals -1, and that's how we will solve for nitrogen equals +5. We have more examples of this later, but this is just showing you that when nitrogen is +5 and we're adding it to the 3 oxygens, it's going to equal -1, the charge of the polyatomic. So if we have a neutral compound, it's going to equal 0. If we have a polyatomic, all of their oxidation states are going to equal the charge on the ion. Our next rule is group 1 metals have an oxidation state of +1 in all their compounds. So like sodium, potassium, lithium, rubidium, they're all going to have an oxidation state of +1. The group 2 metals, those alkaline earth metals, they will all have an oxidation state of +2 in their compounds. So like magnesium and calcium and strontium, all those guys. In their compounds, non-metals will have oxidation states in the table below, and it's in order of priority. So you're going to follow this rule before you follow this rule before you follow this rule, right? So like fluorine is always going to have a -1 oxidation state. Hydrogen will always have a +1 oxidation state. Oxygen will usually have a -2 oxidation state. Our only exception is in hydrogen peroxide or in other peroxides. And if we look, right, hydrogen has a +1. So if we have 2 +1s, and we have 2, and I'm just going to put oxygen as X here, and this is a neutral compound, so it's going to equal 0. So we have 2 + 2x equals 0, right? And then we have 2x equals -2, so x equals -1. So hydrogen peroxide, right, when we have that, that means our oxygen is going to have a -1 oxidation state. All other times, though, oxygen is a -2. So these three rules, this fluorine, hydrogen, and oxygen, those are pretty much always going to be true, like I said, except for, peroxides. And then sometimes you'll have to solve for things in 7A, 6A, and 5A. So like before, right, we saw nitrogen in this other example was a +5, and here it says nitrogen can be a -3, right? So these are going to be followed in order of priority. So in this case, since we had an oxygen is higher on the priority list, so we use the oxygen to figure out the nitrogen. Okay, so that's what's happening there. So like I said, use fluorine, hydrogen, and oxygen. Those three rules, along with the group 1 and group 2 metals, if you follow those rules, you'll pretty much be able to solve for all of the other ones. Sometimes you need this group 7A rule as well, and if you do, then you'll use it as a -1. So here are the oxidation states of main group elements, right? So excluding the transition metals. So as you can see, the alkali metals are always going to be +1. The alkaline earth metals are always going to be +2. These guys are going to be +3. But all of the other ones can change. Even hydrogen, sometimes hydrogen will be a -1, like in the, if we had like calcium hydride, you can have hydrogen making a -1 there because calcium is a +2. So that means hydrogen has to be a -1 to balance it out. But all of these other ones, like these can be ranging from +4 to -4. This has +5 to -3, +6 to -2, right? +7 to -1, so they can change. So we will use the group 1A, group 2A, sometimes group 3A, and usually hydrogen to figure out all of these other ones. And again, like I said, you'll solve it like a mathematical equation. So here's an example. We're going to figure out the oxidation numbers of each element in these compounds. If you want to go ahead and work this out for yourself, you can. So you would just pause here and then work it out, and then come back when you're ready. Okay, so for this first one, zinc chloride. So we have zinc chloride. Zinc is one that we always know the charge of. The reason that transition metals weren't included on the previous slide is because a lot of them have multiple charges. Zinc, though, will always have a 2+ charge, so we know that zinc is going to be +2, which means that chlorine, right, if we have +2 here, and then we have 2, and I'm going to use X again, right, for our chlorines, and that's going to equal 0 because this is a neutral compound. So we'll move that 2 over, so we get 2x equals -2, and so x equals -1, so that means chlorine is a -1 charge. Okay, so that's going to be zinc is a +2, chlorine's a -1. Sulfur trioxide, so that's SO3. And remember, sulfur is one of them that can change. So we'll use the oxygen to figure out the oxidation state of the sulfur. So if we were going to write a compound, we can put, X plus 3 times each of those oxygens is -2. And again, that's a neutral molecule, so that's going to be equal to 0. So we can say, okay, then X minus 6 equals 0, X equals +6. So our answer would be that oxygen is a -2 and sulfur is a +6. Next one, nitric acid. So nitric acid, right, I ate something icky. That came from nitrate, which is NO3 minus, so nitric acid is HNO3. So in this, we'll follow the rules, right? Hydrogen is always going to be a +1 unless it's bonded to a metal. And oxygen is always going to be a -2, and we'll use those hydrogen and oxygen to figure out what the nitrogen is. So we can write our equation again. So we have hydrogen is a +1, plus we don't know nitrogen, plus 3 times each of those oxygens is worth -2. And again, this is neutral, so we put that equal to 0. So we have, -6 from the oxygens and +1, so we get X minus 5 equals 0, or X equals +5. So our answer here is that nitrogen is +5, hydrogen is +1, and oxygen is -2. And then finally, the sulfite ion. So sulfite is SO3 2-. So we're going to use that to solve for the sulfur. So we don't know sulfur. We know each of the 3 oxygens is worth -2, and now this isn't equal to 0 anymore because it's a polyatomic. So now we're going to say it equals the charge of the polyatomic, which is -2. So we get X minus 6 equals -2, or sulfur equals +4. So sulfur is +4 and oxygen is -2. So like I said, I would always try and set it up like this where it's a math problem. Typically you end up in this class because you're good at math. So if you can make an equation, that usually makes people feel more comfortable. Okay, so now we can use this to actually determine whether something is a redox reaction or not. Not all reactions are redox reactions. And so I may ask you on a quiz or a test to figure out which one of the reactions is a redox reaction, and you'll need to find the one in which the oxidation states are changing. Okay, so in this example, we have, where are all my charges? Oh, my charges didn't come through. Okay, that's all right. So if we have this example, sodium plus chlorine reacts to form sodium chloride. When they're by themselves, right, sodium is going to be a 0 and chlorine is a 0, even though it's a diatomic, right? Chlorine is just bonded to itself, so it's a 0. In the compound here, sodium is going to be a +1 and chlorine is a -1. Because these are, it's bonded to a metal, right? Because this is an ionic compound, right? That nonmetal is bonded to a metal, we can break this apart into its ions, Na+ and Cl-. And so sodium's a 1+, so it gets a +1, chlorine's a 1-, so it gets a -1. If we look at the individual half reactions, so we look at what sodium's doing by itself and we look at what chlorine's doing by itself. Sodium went through and became Na+, and it lost an electron. So sodium went from a 0 to a +1. So it changed its oxidation state. On the left-hand side of the reaction, it had a 0 oxidation state, and on the right-hand side of the reaction, it had a +1 oxidation state. So it has changed oxidation states during the reaction. This is going to tell you that this is a redox reaction because the oxidation states changed on the sides of the reaction. Same for chlorine. If we write a half reaction that just deals with chlorine, chlorine gained an electron to form Cl-. Okay, so on the left-hand side, chlorine had a 0 oxidation state, and on the right-hand side, it has a -1. Chlorine changed oxidation states during the reaction, which tells you that this is a redox reaction. So, which one is oxidized, which one is reduced? So sodium is the one, sorry to have to keep writing these all in, but sodium is the one that lost an electron. Sodium went from an Na to an Na+, right? It went from a 0 to a 1+. It became positive, which means that it lost an electron. So sodium is oxidized. Be careful here. A lot of people will see this +1 and they'll forget that electrons are negative and they'll be like, look, it gained an electron because it made a +1, so it's been reduced. No, electrons are negative, so if it became positive, that means the protons are outweighing the electrons, right? It lost an electron. So if it became positive, it lost an electron, therefore it has been oxidized. And the chlorine, on the other hand, the chlorine gained an electron to become Cl-, so that means the chlorine is being reduced. And again, same problem, people see the -1, they're like, it lost one, it's been oxidized. Nope, electrons are negative, which means if it became negative, that means it's gaining electrons, therefore it is being reduced. So be really, really careful with that. So here's an example of a redox reaction. And sorry this got written in all caps. So magnesium metal, magnesium by itself, right, not charged, reacts with an aqueous solution of copper. And when that happens, it will actually transfer electrons, right? And the magnesium will give 2 of its electrons to the copper and will plate it out. This is a redox reaction. And the way that we can tell that it's a redox reaction is that on the left, right, magnesium has an oxidation state of 0, and on the right, it has an oxidation state of +2. Copper on the left has an oxidation state of +2, and copper on the right has an oxidation state of 0 because it's an element by itself. So electrons have been transferred during this reaction, right? They've gone from the magnesium to the copper. And this actually causes a really cool reaction, like when you see it in person. What's happened is there's magnesium strips. These are the magnesium strips here, and the copper solution. And during the reaction, as the electrons are being shifted from the magnesium to the copper copper will actually form down at the bottom here. The copper will form a solid, and the magnesium will start to dissolve. That's why we see the color change. It's actually really cool. But so let's go and talk about oxidizing and reducing agents. So if we have an oxidizing agent, it's causing another substance to be oxidized. So the oxidizing agent is actually doing the oxidizing. So the oxidizing agent is causing something else to be oxidized, which means it is being reduced. If you think this is confusing, you're right. But the reason that we need to cover it is because if you buy a chemical, it's going to tell you oxidizing agent. It's not going to tell you this thing gets reduced, right? It's going to tell you that it is an oxidizing agent, which means that if you react it with something, it will cause something else to be oxidized. It will make something else oxidized. So it will get reduced. So same kind of theory. If you buy something and it says reducing agent, that means it will cause something else to be reduced and it will end up being oxidized, right? Because they always happen in pairs. If something else is being reduced, then that means it is being oxidized. So if we think back to this example that we were just working with, okay, so magnesium went from a 0 to a +2, and copper is going from a +2 to a 0. So magnesium, right, is losing electrons. So remember, losing electrons equals oxidation, right? Leo says Gur, or oil rig. So that means the magnesium is being oxidized, and that makes magnesium the reducing agent, okay? And then copper is gaining electrons, which means it is being reduced, which makes it the oxidizing agent. So yay us. So the oxidizing agent, right, is the one being reduced, so that will be the copper. The reducing agent is the one being oxidized, so that will be the magnesium. And actually here, to be specific, we're usually going to put the ones on the left, right? So magnesium is the one that's the reducing agent because it's being oxidized, and copper 2+ is the oxidizing agent because it is being reduced. Good times. You're going to have to work on that one a little bit. This is something that people struggle with, getting that terminology right. The first step will be to figure out which one's being oxidized, which one's being reduced, and then go and remember that, you know, the oxidizing agent is causing something else to be oxidized, therefore it itself is being reduced. So, in general, if we have X and Y, right, and we're transferring our electrons over there, that means X is losing electrons, right? X is giving electrons to Y, and so Y is gaining them. This means that X is being oxidized because it's losing electrons, Y is being reduced because it's gaining electrons. If X is oxidized, that makes it the reducing agent because it caused Y to be reduced. Therefore, Y is the oxidizing agent because it caused X to be oxidized. X will increase its oxidation number, right? So like X will go from a 0 to a +1, and Y will decrease its oxidation number. Like it might go from a 0 to a -1. So again, like I was saying before, not all reactions are redox reactions. And the way that we will figure out whether something is redox or not is we need to have oxidation numbers that change during the reaction. And the only way to go through and figure this out is to figure out the oxidation numbers of everything before and after the reaction, which is a little bit cumbersome, and it'll be a fair amount of work until you get used to it, but that's the best way to go. If any of the species ends up being oxidized or reduced in a reaction, then that reaction's a redox reaction. So if anything changes oxidation state from the left side of the reaction to the right side of the reaction, then it's a redox reaction. So here are reactions that are not redox, right? If we look and we break this apart, oh, and it's not going to carry my charges again. So if we break this all apart here, let me fill in my charges real quick. So if you look at the charges, right, or the oxidation states on the left and the right, silver is a +1 on both sides, nitrogen's a +5 on both sides, oxygen's a -2 on both sides, we have sodium as a +1 and chlorine as a -1. Things have moved around, right? Things have reacted to form new compounds, they've moved, but the oxidation states are all the same. Therefore, this is not a redox reaction. Same thing here in this reaction. If we look, sodium, right, has a +1 on both sides, oxygen has a -2 on both sides, hydrogen has a +1, and sulfur has a +6 on both sides. So the oxidation states for all of these elements are staying constant throughout the entire reaction. There is no change in oxidation states, therefore this is not a redox reaction. So again, the only way to figure this out though is to go through and assign all of these individual oxidation numbers to see, is something changing oxidation states? And again, if it is, then it's a redox reaction. If it's not, then it's not a redox reaction. We have one last kind of type of redox reaction, and this is called a disproportionation reaction. And this is when a portion of the reactant is oxidized and a portion of that same reactant is reduced. And it'll usually look like this. It'll usually be these decomposition reactions in which you're seeing it. So on the left, we have hydrogen being a +1. And again, remember that when oxygen is in a peroxide like this, it's going to be a -1. If we look at hydrogen on the left, hydrogen is still a +1 in water, but oxygen now is a -2. But oxygen over here, when it's sitting by itself, is a 0. So we have oxygen being reduced, right, because it gains an electron, and we have oxygen being oxidized because it loses an electron. So this is how we see a disproportionation reaction. Oxygen is being both oxidized and reduced during this same reaction. So this is a disproportionation reaction, okay? Some of it's oxidized, some of it's reduced. But it's this oxygen, right, that's doing both. Hydrogen has the same oxidation state on both sides of the reaction. Hydrogen doesn't change, just oxygen. And our last topic of today is metals as reducing agents. So this is called the activity series, and this will dictate whether or not the reaction actually happens. If we have a metal that's high on the activity series, that means it's really, really reactive. If we have a metal that's low on the reactivity series, then it's not very reactive. And so not all reactions just kind of happen, right? Just because we mix two things together doesn't mean a reaction will occur. So we need to figure out where these metals lie on the activity series to figure out whether or not a reaction will happen. For example, if we have zinc reacting with hydrochloric acid, we find zinc, so here's zinc. So zinc lies above hydrogen in the activity series, which means zinc will replace hydrogen in a compound. Zinc will kick hydrogen out, right? Like zinc, you can think of zinc being stronger than the hydrogen, right? So it will kick hydrogen out of there and it will bond with the chlorine and leave hydrogen by itself. If though, say we had copper reacting with hydrochloric acid, because copper lies below hydrogen on the activity series, this reaction will not occur, okay? Copper is not reactive enough, it's not strong enough to kick that hydrogen out of that hydrochloric acid, so nothing will happen. You can have copper just sit in the hydrochloric acid, happy as can be. Okay, so that's why this activity series is important. You can figure out whether or not a reaction will actually occur. So you need to have this activity series memorized. And the way that you can remember it is I wrote this clever little mnemonic over here. So this says, please stop calling me a careless zebra. Instead, try learning how copper saves gold. And that will help you remember potassium, sodium, calcium, magnesium, aluminum, carbon, zinc, iron, tin, lead, hydrogen, copper, silver, gold. Okay, that is the activity series. You can remember it however you like, but I think this is fun. Please stop calling me a careless zebra. Instead, try learning how copper saves gold. And again, you need to know this. You need to have this memorized so that you can figure out whether or not a reaction will occur as written. And that is the end of this set of slides. So today we talked about redox reactions, we talked about determining oxidation states, we talked a little bit about disproportionation reactions, and of course, the activity series. Make sure you're getting practice on this on that Chapter 4 lecture worksheet, and as always, send me any questions if you have them, and I will see you next time.